The energy transition is a really important topic because energy isn't that everywhere available good. And I think with decreasing invest costs on lithium-ion batteries, it would be more easy to apply them as a decentral energy storage for renewable energy plants. I do my research on the production of lithium-ion batteries because the manufacturing process is too expensive until now. And we want to increase the production capacities and production speeds to decrease the costs. My name is Marcel Schmidt. I studied process engineering at the KIT in Karlsruhe, the former University of Karlsruhe. And I did my diploma thesis on the slot die coating of organic photovoltaics. And that's where I get into this topic. In our TFT coating and printing lab, we have the capabilities to coat from the smallest scale of, for example, organic electronics to a larger scale lithium-ion batteries on pilot plants. In general, there are some PhD students together with master thesis students, bachelor thesis students, or also some auxiliary students. The students in the lab are kind of a driving force of our working group. They bring in new ideas, fresh ideas, and also manpower, of course. And the colleagues are doing research on scalation of dryers, and they want to investigate how your morphology develops during the coating. They want to build up some simulation models to calculate such effects in before. Lithium-ion batteries are made of several really thin layers, and like every other battery we have a cathode, separator and anode. They are built up porous, so an ion-conducting electrolyte defines a continuous phase through the whole system. So these very thin layers of the electrodes have to be processed from a wet film, and therefore you have to mix your ingredients into a stable slurry. This slurry has to be coated as a thin film, like you see here, onto a metal foil. And then these films have to be dried, have to be calendared, cut it out as single electrode sheets, and then stacked to a cell together, packed, filled with electrolyte, and then formated in some few cycles. My research topic is the coating of these slurries onto the metal foil. Being more precise, we use a pre-meter coating method, like the slot die coating. Here you have an inlet where you give a very defined liquid flow. You have a distribution chamber and a small slot where you get a pressure drop. And within this pressure drop, we get a well distribution of the liquid flow over the slot width. And here it's really important to form a stable coating bead between the die lips and the substrate you want to coat on. This coating bead forms your film and has to be stable. To start our coating, we then put the bypass valve in direction of the waste pipe. First, build up a steady state pressure, and then we check our slot die if the lips are clean. We go to our pre-adjusted gap and then just switch the bypass valve and start the coating. At the start of the coating, we see there's a starting phase where we have to build up the pressure inside the die. And we first have to put energy in there, which gets stored inside the slurry. So if we reach a steady state pressure also in the die, we then have a stable coating bead where we can coat continuously very smooth and homogeneous films. During the calendering, your film gets compacted, your energy density increases and your adhesion force increases, but your metal foil beneath your coating also gets stretched. And the metal foil at the edge region, where you won't have a coating, isn't stretched. So here in the intersection you will get some tensions and some folds, and these folds may provoke a film peeling or an uneven handling in the downstream processes. So one possibility to avoid these folds could be cutting off the edges before the calendering. But for a stacked cell design you need some uncoated areas where you place your current arresters in the later on cell, which avoid this cutoff. If you coat intermittently, you can place these uncoated areas, these current arresters, in between the coating gaps, and therefore you can cut off your edge and get a proper calendering. We are doing research on this intermittent coating, and we want to go to a new technology where you can easily increase your coating speeds, again to decrease your costs, and therefore we won't apply already available technologies where you have to move your slot die or to move your web. That would only cost time and cause vibrations in your film. We did some investigations about the interior slot die design where you can stop and start your coating in cooperation with a bypass valve, and with that you get a proper intermittent flow. During the lunch break we can use our sun terrace where we discuss over the results of the morning and how we go on in the afternoon, and that works very well together with a coffee. So until now we could show that we can coat at 100 meters per minute, which is a limit experts say you don't have to go beyond, because the costs won't decrease that much as your plant costs will increase. For the intermittent coating we developed a technology where we can coat intermittently very proper with defined and sharp edges, and this technology is also capable on really high coating speeds where we also can replace our bypass valve. Until last year we used a LabVIEW application to control our valves and our intermittent coating, but our lab PC always did something else than just focused on that topic. And my student Ralph came to me and told me something about the open source Arduino microcontrollers, and we just ordered a lot of them and some spare parts to build in, like relays and transistors, and we then applied them onto our intermittent coating and just sending one string from our LabVIEW to the Arduino, and the microcontroller runs until the end of time. So the idea for this intermittent technology came in origin from me, but all the students working on that topic brought this project really forward. So the result we see today is some kind of result of a teamwork. So I'm really open for new ideas, and that's an example for all the small things we are developing in the lab, and we are just thinking about in the office how can we improve our everyday work. Next year, in August 2015, I want to be finished with my PhD at the KIT, and until then I have to publish some of the results and to combine them to a PhD. And afterwards I would like to go to a worldwide acting company where I can share my knowledge and give a contribution to the public.